Up above that line, we have a liquid solution. Down below that line, we have a solid solution. That is, we mix the two things together, and we still just get one phase. There's nothing we can separate out of that as an entity, either optically or mechanically. Well, we get this diagram from cooling curves. And in fact, the cooling curve that we would get would be that as we cool the material off when we got to the temperature C, then the temperature would actually hesitate for a moment. We change the slope of the cooling curve. And the slope would be changed until we got to the solidus, and then the slope would change again. So we don't get abrupt points like we did in pure metals. They're just breaks in the curve. Now this particular diagram gives us all sorts of problems and all sorts of nice things to talk about. So I want to stop now and tell you some new words. Sometimes when we solidify a metal, and the metal solidifies, it does so by growing just like a tree. And so we wind up with a tree-like structure. We have a word for that, and the word is dendrite. D-E-N-D-R-I-T-E. A dendron is a Greek word for tree, and dendrite means a tree-like structure. So it's an imitative shape name. And sometimes when we solidify a metal, it'll grow just like a tree. So let's imagine that we're in a big crucible of say, zinc. And right where my feet are is a cold spot. And what will happen is that the material will start solidifying at that cold spot. It's the nucleus. And it'll grow right up as a trunk of a tree. And then that trunk will have branches. The branch will have limbs. The limbs will have twigs. And if I could suck all the molten metal off just like that, then I'd have standing up there a solid tree. That says the mixture of the liquid and solid now was a tree-like solid with liquid all around it. So if I poured it all off, I'd have the tree. Now let me ask you this. Did you ever see a tree like that? He's an Amos. I know he's an Amos. On this one, let me ask you this question. Did you ever see a brand new metal garbage can? Did it sort of scintillate, sort of wink at you when you went by? Right? And you didn't care? You know, Bill Shakespeare wrote something in As You Like It. I think these are the most wonderful lines. So wonderful I have them hanging in my hall. It says, "And this our life exempt from public haunt finds summers and stones, tongues in trees, books in running brooks, and good in everything." And that's really so. Hey, what he was trying to tell us is, don't be an Amos. Hey, wake up, nature will talk to you. And so these trees, I know you see all the time, because you see in that galvanizing operation, they took the piece of steel, the can, they shoved it down in a pot of molten zinc, they pulled it out, and the tree of zinc is growing like mad, and the molten zinc is running off of it by gravity. And it leaves delineated in relief these particular little structures. I have a piece of galvanized iron here, and if we can see it in a close-up on this particular piece, you'll be able to see that there are little trees that define the crystals. We see the crystals now not because we delineated them by etching, let's say, or by the chemical anisotropy. We see them now because we have these actual points in here, the little tree branches that you can see growing out like this. Growing out, and they have branches in between everywhere. So this is the appearance of galvanized steel, and I know everybody's seen galvanized steel. All right, let's get back now to the solid solution thermal equilibrium diagram. If we do that, we say, what really happens now, if we looked at that last slide, and we say, what really happens when we start solidification? Well, if we have an alloy, and the alloy is this particular alloy, let's say about right in the middle of the diagram, 50-50, when we got to this particular point, the first material that's going to solidify is going to be the material which at that temperature is solid. And we just draw over here and we find that's the composition of the solid. And so this is the composition of the bucket of material that we have to start with. But it's going to start solidifying something that's over here. If we drop the temperature a little bit lower, then the solid is going to be this solid. It will come down. And the liquid will be down here. Still lower, it will be here for the solid and way over here for the liquid. And so we move on this particular equilibrium diagram from one point to another just by solidifying, and inside of this bucket of metal we're segregating the material. We are causing the dendrite that is solidifying first, the little tree, will be one composition. The limbs and branches are going to be another composition. So when we're all through, we didn't decant the metal, but we can go back and etch the surface, and we looked at that etched surface, and because it's different chemically, we see we have dendritic segregation. Ha! Now, suppose you're designing, and you have a copper-nickel alloy, and you say, I want to know what its grain size is, I want to know what its mechanical characterization is, and I ought to know this now, but you look in the microscope and you find out you got segregation. You don't have an alloy of one composition anymore. You have an alloy that's microscopically segregated. So is it possible to get it all back like it's supposed to be? The answer is yes, because again, if you go back to this diagram now and look at it, you find out that we have underneath, all down here, one phase. So that says if I kept the temperature right there for an exceptionally long period of time, then I would have a solid solution. Just one thing. I can eradicate or do away with or wipe out the effects of the dendritic solidification mechanism. And someone asked me earlier today, hey, what's all this business about powdered metals? Why are we so interested in powdered metals? Well, here's one reason we're interested, because if I want to make a big casting, let's suppose I want to make, something like an impeller for a jet engine, and I want to cast it. If I make that big casting, I'm going to have segregation in it. But if I could make it as a tiny little droplet, I could go from the liquid state to the solid state so fast that it wouldn't segregate. It wouldn't have a chance to diffuse to segregate. So I can get little tiny droplets or little particles of the solid metal, dust so to speak, or metal powders, which are homogeneous. And I can put all those homogeneous particles together, and if I can cause them to bond, and we can, then I have a piece in which I didn't have to do the heat treatment to get it to be homogenized, because those heat treatments take an awful long time. And so we find out this equilibrium diagram now is telling us a big story.
An ideal cooling curve shows the temperature behavior of a metal as it is heated and allowed to cool by plotting time versus temperature. An actual cooling curve shows that the temperature of the molten metal will dip below its solidification temperature before returning to that temperature. This is called supercooling. A solution contains two liquids, called phases, mixed together but not dissolved in each other. A phase is a mechanically separable or optically identifiable part of the system. It is possible to have a solid solution, a region where two phases exist. Phase diagrams allow us to calculate the amount of each material present in a specific composition by means of the lever rule. Dendrites are tree-like structures that can readily be seen on galvanized steel. Sometimes, as a metal solidifies, it grows in this manner. Alloys may exhibit dendritic segregation, which occurs when one element becomes the trunk and another element becomes the branches of the dendrite.
Well, in the next slide, we find out that we can do all sorts of tricks, and we do something that's called purification. This is one end of the diagram. It's the nickel-rich end, and we find out now that if we want to, we can say examine one temperature to find out what the material is we're going to solidify. So if we look at the point on temperature that's marked about, I think it's 1400 degrees C, right here, we find that at that particular temperature now, when we start to solidify, that's the material that's going to come out. Do you notice that that's more nearly pure nickel than the alloy we started with, which was right through here, right? It's closer to the nickel line. That says if I were to solidify the material, the first material to be solidified is going to be purer than any later material, because down here at this temperature, this is the composition of the alloy now. That's what's in the pot. And at this temperature, that's the liquid that's going to be coming out, and the solid that's going to be coming out. And the liquid composition will be way over here. So the solid composition is going to vary from here all the way over to some point that's way over here when we're all through. This enables us now to take something like a piece of aluminum that has impurities in it, and we can exclude the impurities just by solidification. Did you know that before? Yeah, I bet he's an Amos. Because you see, it has an exact analog in water. I call this barroom 1. You know, you can study a lot about materials in just things around you. But next time you sit down with a cup of ice, you pay attention to the cup of ice, and it'll talk to you. And here's the reason it will. The first material that we start with is going to be the water. Water will dissolve about 20 cc's of air per liter of water. It's impossible to have a glass of water sitting on the table and say, that's pure water. I don't care whether it's distilled or not. If it sits on the table, it's going to dissolve 20 cc's of air for every liter of water. If we solidify that water, in the solid state, the water has no solubility for the air. So it burps it out. And it's going to be growing by dendritic growth. And as it burps out, the little bubble of air is going to get caught up in the branches of the dendrite. And then the solidification will move a little bit, and it burps out a little bit more air. And so the little air bubbles that go through the ice, and they're in the line. We call them air worms in the ice, right? And that's all because now of the fact that the first material to solidify is the pure material, is the water, right? And the last material to solidify is going to be that with the impurity in it. Or sometimes you see such things as cubes of ice or cakes of ice that have a brown material inside. That's generally something like iron hydroxide that has been pushed out as an impurity as the material solidifies. So solidification is a method of purification. Now, if we looked on the other end of the diagram, we'd find that that didn't quite work, and that the first material to solidify in that case is going to be the pure material. The impure material. And the liquid that's left is going to be the pure material. And so if we take tin on the other end of a diagram, it looks like that. If we heat the whole mass up, then the liquid tin runs off as the pure tin. If it's on the other end of a diagram, it looks like that. And we call that purification by liquefaction. All right, let's look at another kind of a system now. And we find that everything doesn't look like a solid solution. And in fact, you can find text, the text that was given to you, the reference book that was given to you, in the very back of it you'll find is loaded with equilibrium diagrams, all different types, and there are texts that talk about how many different types of equilibrium diagrams you can have. I think there are only 4 basic types. And this is another one of the basic types. In this particular case, it says if I mix with the material copper over on this side, the material silver that's on that side, and get a composition that's right here. So by the inverse lever rule, I would have a material that's about 70% silver in this case. If I take that particular material, it has a singularity of melting. One melting temperature. It melts and solidifies right there at that temperature, at this temperature. If I had an alloy over here, then the material would start to liquefy here. If I was heating it up, it would finish liquefying there, all be liquid above. If I cooled it off, it would start solidifying here and finish solidifying there. But in this kind of a diagram now, we have a uniqueness. We have one composition that has a singular melting point, and it's going to act just like a pure metal, just like a pure substance that has this one singular melting point. When I went to college, I asked my professor, will you tell me why it is that that point, which is called the eutectic melting temperature, or the eutectic composition, why is it that the eutectic has the lowest melting point in this whole series? Because you notice that the melting point of the eutectic is here, the melting point of the silver is there, and the melting point of the copper is way up there. So here we mix them together and we get this very low melting point. Well, number one, he says, you know all about that, because you know but putting antifreeze or alcohol in your radiator, right? Lowers the melting point. In this